So we're going to do a problem, nice kind of classic problem using the form of Ohm's law that we just wrote down. This is rather similar to one of the examples done in Griffiths. I think Griffiths does it for a couple of cylinders. We're going to study two spheres, and we're going to have a sphere, two concentric spheres. First sphere will have radius A. Second sphere has radius. Oh, let's clean that up. There we go. Second sphere has radius B, and we're going to fill the region between the spheres with a material that has conductivity sigma. So current can flow from the inside sphere to the outside sphere through this material that has conductivity sigma, and we're going to give the inside sphere potential V, and we're going to ground the outside sphere, so this is at V equals 0, and we're going to ask the question, how much current flows between these two? Okay, so we're going to use our relationship J equals sigma E to solve this problem. But the first thing that we're going to need is the electric field, and the problem has been specified with two boundary conditions on the two spheres. So first of all, let's solve for the potential in the region between the spheres. Well, we know that the potential between the spheres is of the form B divided by R plus C, where B and C are both constants, and we have two boundary conditions. So one of those boundary conditions is at R equals A, so we can write down that V at A Okay, so we have these two boundary conditions, and we can use those to solve for the two constants B and C, and I'll leave you to do that. But the two constants that you get are the following. You'll get that B is the following. Okay, so there's our result. And of course, you should do immediately when you get a result like this, you should do the usual checks. First thing we would check is that the units are correct. Let's have a look at that. Well, here we've got a potential on the left-hand side, and here on the right-hand side, I have a potential multiplied by a length squared and divided by a length squared, so that's okay. And here I have a potential times a length divided by a length. So units are okay. And the second thing that you should check is that it does indeed satisfy the boundary conditions, and you'll find that it does if you check that. Okay, so now we have our form for the potential. Now, of course, the electric field is the gradient of the potential, and we would need to do that in spherical coordinates, but that's straightforward. So we would write the following. So this is our electric field, and now we're going to use Ohm's law in the form that we wrote it down in the previous segment to give us the current density. And then to calculate the total current, what we're going to do is we're going to take the integral of J dot dA. We're going to integrate it out over a sphere of radius R. So the integral there, the angular part, is just going to be 4 pi. And then I'm going to take J, of course, J is parallel to the area element. J is in the r hat direction. The area element on the surface of a sphere is also in the r hat direction. So we would wind up with the following expression then. We have to have a sigma, don't we? Sigma. All right, and of course the r squareds in the area element, cancel the r squared here, as it must, right? This result must be independent of r, otherwise we would have some serious trouble. We would have current being created or destroyed, and we wind up then with the following result. Okay, so let's just study this result just briefly. These constants here are the reciprocal of the resistance. All right, so the total resistance of the material between the two spheres. Now, you can now study this in a variety of limits. If A equals B, the resistance goes to 0. Remember, the resistance is the reciprocal of this number. So if A equals B, the resistance goes to 0. That makes sense. And you can do a bunch of other checks of this kind and convince yourself that this is indeed the right form for the resistance. Let's just write the resistance out over here. Okay, so there is the resistance. If you want to see a similar example, you can have a look in Griffiths. He does it in cylindrical coordinates. So this is just an example of how to use that form of Gauss. How to use that form of Ohm's law that we wrote down in the previous segment.